Hi guys, welcome to today's lesson on basic probability. So as you can see today, our goal is going to be to calculate basic probabilities, but also distinguish between what we call experimental and theoretical probability. So here's our agenda. There's going to be a lot of vocab today, just so you know. We're going to go through some basic probability along with that vocab, and then we're going to talk about theoretical, experimental probabilities, and then we're going to finish up with some dice problems, some practice problems, all right? So first thing, like I said, we have some vocab. Feel free to kind of pause the video as I go through and then unpause so that you can get all these words down. So first word is outcome, the word outcome. So an outcome is a possible result of an experiment. So an experiment could be something like rolling a die, flipping a coin, spinning a spinner, picking a person out of a classroom and identifying what color hair they have. Anything like that, okay? So an outcome is a possible result. So for example, if I'm flipping a coin, my possible results, if I'm flipping a coin, could be either heads or tails, right? If I'm picking a person out of a classroom and looking for hair color, I could have someone with brown hair, I could have someone with blonde hair, I could have someone with black hair, red hair, etc., right? Okay, if I'm rolling a die, my outcomes could be 1, 2, 3, 4, 5, or 6. So let's move on. Next word is an event. So an event is one outcome or a collection of outcomes. So for example, we said if I'm rolling a die, up here the outcomes of rolling a die could be getting a 1, 2, 3, 4, 5, or 6. Those are the individual outcomes. So an event could be rolling a 3, okay? So an event could be roll a 3, or it could be a collection of outcomes. So rolling an odd number, that means rolling a 1, 3, or a 5, right? It could be picking someone with dark hair or like brown or black hair if I pick my person, something like that, all right? Next vocab word is sample space. So the sample space is the set of all possible outcomes. So typically when we list our sample space, again, we're listing all possible outcomes, and we typically list it in what's called a curly bracket. I know sometimes those are hard to make, just do the best you can. But if I'm talking about rolling a die, the sample space would be rolling a 1, a 2, a 3, a 4, a 5, or a 6, right? If I'm talking about flipping a coin, my sample space would be either getting a heads or a tail. If I'm talking about, um, playing a baseball game and who wins the baseball game, all possible outcomes would be either, let's say, like the home team or the away team. One of them has to be the winner, right? So that's sample space. Okay, probability of an event. The probability of an event is a measure of the likelihood or chance that the event will occur. So you probably already know a little bit about probability. If something is definitely going to happen, think about what probability that event has. If something is definitely going to happen, we say there's a 100% chance of that event occurring. For example, there's a 100% chance that math is going to be your favorite subject this year, I hope. Something like that, okay? If something is never going to happen, the chance of that, we say that it has probability of being 0. All right? Okay, so let's get into an example. You toss 3 coins. How many possible outcomes are there? List the possible outcomes. And remember, we just said that the possible outcomes, we call that the sample space, all right? So if I toss 3 coins, I could get a heads on the first coin, a heads on the second coin, and then a heads on the third coin, right? So I could get all 3 tosses being heads. Let me make this a little bit clearer. Sorry. So heads, heads, heads. Or I could get my first one is a heads, my second one is a heads, but my third one could be a tails, right? Instead of that third one being a head. Or my first one could be a heads, then my second one could be a tails, and my third one could be a heads. Or if my first one's a heads and my second one's a tail, my third one could then also be a tail, right? Now, is there any other combination? Notice I'm doing what's called making an organized list. Is there any other combination that I could possibly have if I flipped a head first? No, this is it, right? If I flip a head first, it's either one of these 4 options. But what if I went and I flipped a tail first? I could get a tail and then a head and a head, right? Or I could get a tail and then a head, and then what else? A tail. Or I could get a tail, and then a head. Or a tail, 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 right? So these are all the possible outcomes. This is my sample space. Again, my sample space is all possible outcomes. Then I'm asking you, how many possible outcomes are there? Well, let's count these. 1, 2, 3, 4, 5, 6, 7, 8. So the answer to this question, I have 8 possible outcomes in my sample space. All right. So now here's a problem that I want you to pause the video and I want you to try, okay? And then when you're finished listing out your sample space and determining how many possible outcomes there are, you can unpause the video and then check your answer with me. All right, so hopefully you thought about this. The spinner has 5 congruent spaces, numbers 1 through 5. So those possible outcomes would be 1 through 5, right? You spin the spinner and then you toss a coin as well. Well, if you toss a coin, you could either get a head or a tail. So you can see I listed all my possible outcomes, or in other words, I listed my entire sample space here. I could get a 1 on the spinner and a head on the coin, or a 2 on the spinner and a head on the coin, etc., etc., etc. So how many possible outcomes are there? If I count these all up, I'm going to see that I have 10 possible outcomes, right? Now, I want to show you something real fast too. This is what's called the multiplication principle. If I'm doing 2 different things, I'm first of all spinning a spinner and then I'm tossing a coin. If I'm doing 2 different things and I want to figure out how many outcomes there are in total, what I can do is I can think about, so like here's my spinner, here's the result of my spinner, and then here's the result of my coin toss. How many different outcomes could I have on my spinner? There's 5 different outcomes on my spinner, right? Well, how many different outcomes could I have on my coin? 2 different outcomes. In order to figure out how many things there are in the sample space, I can just multiply 5 times 2 and get 10. That's what we call the multiplication principle. So I'm going to go back a minute to this problem. I'm tossing 3 coins. So I have 1, 2, 3 coins, right? So it's like, how many different things am I doing? I'm tossing coin 1, and then I'm tossing coin 2, and then I'm tossing coin 3. Well, how many different outcomes could I have on coin 1? Coin 1 could either be heads or tails, right? So I have 2 outcomes. Coin 2 could either be heads or tails, so I have 2 outcomes. Coin 3 could be heads or tails. I have 2 outcomes. If I multiply 2 times 2, I get 4, times 2 again, I get 8. And that multiplication principle is always going to work, all right? So you can always use that to kind of figure out how many things are going to be in your, or how many possible outcomes are going to be in your sample space. All right, new word. So theoretical probability. Notice we're going to have two different kinds of probabilities that we're going to go over. This one's called theoretical. Theoretical sounds like in theory. It's in theory what should happen. So you're not actually going and doing an experiment. You're thinking about in theory what should happen. It's the chances of an event happening based on all the possible outcomes. So the probability of an event, and notice this notation here, we use a capital letter P, and then in parentheses we'll list the event. So for example, if I want to find the probability of rolling a die and getting a 2. So let's say the probability of rolling a 2 on a die. That's how I would write that, all right? Capital P and then in parentheses, rolling a 2. To find that probability, I need the number of favorable outcomes. That means the number of 2s. How many 2s are on a die? I have 1 2 on a die, correct? Divided by the number of possible outcomes. Well, if I roll a die, how many different outcomes are there? In other words, how big is my sample space? So the bottom here, this denominator, the number of possible outcomes, that's my sample space. Well, if I roll a die, I could get a 1, 2, 3, 4, 5, or 6. So the probability of rolling a 2 is 1 out of 6. Now, this is theoretical because did I actually roll a die? I did not, right? This is what would happen in theory if I did roll a die. So we kind of talked about this a little bit ago. Just some important things to remember. The more likely an event is, the closer its probability will be to 1. The less likely an event is, the closer its probability will be to 0. And the probability of an event occurring can never be more than 1. All right. One other thing that you should know, hopefully you know this already, when you list probabilities, you can list them as fractions, you can list them as decimals, or you can list them as percentages. Any of that is fine. All right, so there's your definition for theoretical probability. So let's go through an example. What's the probability of rolling an odd number with 1 die? Okay, so my notation, I'm going to write capital P. This is the probability of rolling an odd number with 1 die. Well, let me go back to my formula. Number of favorable outcomes over number of possible outcomes, right? Or in other words, the sample space. So number of favorable outcomes, rolling an odd number. How many odd numbers are there? When I roll a die, I could roll a 1, a 3, or a 5, right? So that means I have 3 favorable outcomes. How many possible outcomes are there? We just said in the previous example, there's 6 possible outcomes in my sample space when I roll a die. So the probability of rolling an odd number with 1 die is 3 out of 6. Now, if you do give your answer as a fraction, you're always going to reduce that, right? So you could say the probability of rolling an odd number is 1/2. Like I said, you can also make that a decimal, or you can make it a percentage, okay? So here's a you try problem. Pause the video, just take a minute, and then when you come back, you'll have your answer to this one. All right, so you can see that I listed out all of these months, right? What's the probability that the month someone was born in begins with a J? So again, using our notation, capital P, and I want the probability that the month begins with a J, right? So I need the number of favorable outcomes over the number of total possible outcomes. So how many total possible outcomes are there? How many numbers are there in my sample space? Or how many months are there in my sample space? 12, right? So I want to know the probability that someone was born in a month that begins with J. That would be January, June, July, right? So there's 3 out of 12, or in other words, 1 out of 4 months that begin with a J. So that, hopefully you got 1/4. All right, new definition, experimental probability, okay? So kind of like before, we had the word theoretical probability. I heard the word theory in theoretical. Now you can kind of hear and see the word experimental. So experiment. In other words, when I actually go out and do something, the chances of an event happening based on what actually has occurred during an experiment. What actually happened when I rolled a die? What actually happened when I flipped a coin? Whatever that might be. So again, the same notation, probability of an event is the number of times the event actually occurred over the number of times the experiment is done. Okay, so now that we have the definition of experimental probability, I want to kind of go through like what this would actually look like, all right? Let's say I wanted to roll a die and I wanted to find the probability of rolling a 5 on a die, let's say, okay? And I want the experimental probability. Remember, this is based upon what actually happened, okay? So I need to basically keep track of how many times I roll a 5 and then how many times I roll anything else. So 1, 2, 3, 4, or a 6, okay? So I have this little website here that's going to help us out, and it's going to roll some die for us, okay? So look, I'm going to roll a die. My first outcome was a 3, okay? So I rolled something other than a 5. Now let me roll again. I rolled a 4, so that's something other than a 5. So I'm going to put little like tally marks down here. All right, so then I roll again. I rolled another 3. That's another one down here. Let me roll again. That's a 1, right? Let me roll again. I'm going to roll 10 times. That's another 1. And so I'm up to 5. Here's a 2, right? Here's another 2. There's a 5. All right, so I got a 5. So now I rolled the die 5, 6, 7, 8 times. So I need to roll the die 2 more times to get 10 total. Okay, I don't have to roll 10. That's just what I decided I'm going to do. There's another 5. All right, so now I need to roll one more time. And I get a 1. Okay, so basically I have 2 5s and 1, 2, 3, 4, 5, 6, 7, 8 other things, right? But if I want to know the experimental probability of rolling a 5 based upon this experiment that I just did, it's the number of times the event occurs, right? So I rolled a 5 twice, divided by the number of times the experiment was done. Well, I rolled this die a total of 10 times. So that would be 1 out of 5. That's what that reduces to. So the probability of rolling a 5, the experimental probability of rolling a 5 based upon this experiment I just did is 1 out of 5, right? Okay, next question for you. Will experimental and theoretical probability of an event be the same? Well, if I were to ask you what's the theoretical probability of rolling a 5, hopefully you learned before that that should be 1 out of 6, right? So were they the same? In this case, they weren't, right? The experimental probability was 1 out of 5. The theoretical probability is 1 out of 6. They're going to be pretty close, but they're not going to be exactly the same, right? Because this is real life. This is like what we actually went out and did. This is not in theory. So what should happen in theory versus what happens in real life are sometimes different. Could it just so happen that I roll a die 6 times and get 1 5? Absolutely. So I could have an experiment where the experimental probability was the same as the theoretical, but that's not always going to happen. All right, so here's some example problems that we're going to go through together. All right. Dale conducted a survey of the students in his class to observe the distribution of eye color. The table shows the results of his survey. So you can see all the different eye colors he looked at were blue, brown, green, and hazel. And you can see the counts of how many of each type, or I'm sorry, how many people of each color eye he had. So if you take a minute, we're going to find the experimental probability distribution for each color. So we want the experimental probability, basically what happened based upon his survey or his experiment. So what's the probability that someone had blue eyes? Well, we need the number of favorable outcomes, 12, right? So that probability is going to be 12 over something. It's the number of total times the experiment was run. Well, we need to add up all these numbers here. 12 plus 58 plus 2 plus 8. So take a minute, add those all up, and get your total. Okay, so hopefully you discovered that the total number of students that he surveyed was 80. So the probability, the experimental probability of picking someone with blue eyes should be 12 out of 80. Now how about brown eyes? So we had 58 people with brown eyes out of 80 people. How about green eyes? We had 2 out of 80 people. And how about hazel eyes? We had 8 out of 80, right? So based on the survey, what's the experimental probability that a student in Dale's class has blue or green eyes? So blue or green. So that would be these people and these people, right? Well, I would have these 12, but I would also have these 2. So it would be a total of 14 people that had, again, the number of times an event occurred. We had 14 people that had either blue or green eyes. And the number of times the experiment was done was still 80. So that probability would be 14 out of 80. Based on the survey, what's the experimental probability that a student in Dale's class does not have green or hazel eyes? Let me go back and erase this. So does not have green or hazel eyes. So if we want them to not have green or hazel, what color do we want them to have? Either brown or blue, right? So we can take these two together and add them together. So 12 plus 58, that's going to be 70 out of 80 students that had either, that did not have green or hazel eyes. All right? So take a minute, pause the video, try these problems, and then once you're finished, you can unpause it, check your answers, and I'll talk you through some of these, okay? All right, so hopefully you went through these problems. Here's your answers. Check these real fast. Just some tricky things that I want to review with you real fast, okay? The first section, there's 15 equal size sections, numbers 1 through 15. So the probability of an odd number, you need to go through and count how many odds. 1, 3, 5, etc., until you get up to 15. You'll see that there's 8 of those, where there's only 7 evens, right? Not a 5 would be everything else. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, right? Be careful with less than 5. Less than 5, that would mean either 1, 2, 3, or 4. That would not include 5. Just like greater than 8 would not include 8. If I said greater than or equal to 8, that probability would be 8 out of 15, right? But greater than 8 just means 9 through 15. Okay, 7's pretty straightforward. What's the probability that you'll roll a number less than 5? Again, less than 5 doesn't include 5. The probability, number 8, the probability that a spinner will land on a red section is 1 out of 6. What's the probability that the spinner will not land on a red section? So that's anything else other than the red. Well, if 1 out of 6 is red, the other 5 out of 6 is not red. This one down at the bottom, this is tricky. It tells you that Levon has a bag of candies, and it tells you that there's 20 candies in the bag, 6 red, 5 orange, 3 brown, 2 yellow, and 4 blue, right? And it tells you that she performed, without looking, she chose a candy, recorded the color, and returned the candy to the bag. She performs this experiment 100 times and found that she chose an orange candy 22 times. What's the experimental probability? So based upon what actually happened, how many times did she choose an orange candy? Well, she chose an orange candy 22 out of 100, and when you reduce that, that's 11 out of 50 times. I could have asked you the same exact question, but cross that word off here, experimental, and if I wrote theoretical, what's the theoretical probability of choosing an orange candy? I would go up here and I would say there's 5 orange out of 20. So it would be 5 out of 20, which is 1 out of 4, right? And remember, we said theoretical and experimental probabilities are not always the same. So make sure you are reading carefully so that you know which one we're asking for. All right. So one more kind of type, I guess, different type of problem that I want to show you. Let's look at a common probability problem. So two six-sided dice are rolled, and the sum, remember what sum means? That means that we add the two numbers up. So we add the two numbers up. The sum is calculated. What are the possible outcomes? So if I roll two die and I add them up, what's the smallest number I can get? Think about it. The smallest die is, or the smallest outcome on a die is a 1. So if I get a 1 and a 1, the smallest outcome I could get is a 2, right? And what's the biggest outcome I could get? Well, if I rolled a 6 and a 6, I would get a 12. And I could get any number in between. But here's the thing. Am I equally as likely to get a sum of a 2 as I am, let's say, like a 6 or a 7? There's only one way to get a 2 if I rolled a 1 and a 1. But let's say if I roll a 7. To get a 7, I could roll a 6 and a 1, a 3 and a 4, a 5 and a 2, right? So there's a lot of different ways to get a 7. So what I'm going to do is I'm going to make a table, and you should do the same. And on my table, I'm going to list the possible outcomes. I could roll die 1, and I could roll die 2, and I'm going to roll them separately. When I roll die 1, I could get a 1, a 2, a 3, a 4, a 5, or a 6. When I roll die 2, I could also get a 1, a 2, a 3, a 4, a 5, or a 6, right? But then I'm going to add them. I'm going to sum the two die. So if I get a 1 and a 1, my sum is, let me change the color here. My sum is going to be a 2. If I get a 2 on die 1 and a 1 on die 2, my sum is a 3. If I had a 3 and a 1, my sum would be a 4. A 4 and a 1, my sum would be a 5. A 5 and a 1, my sum would be a 6. And a 6 and a 1, my sum would be a 7, right? And then I'm going to keep going. If I got a 1 on die 1 and a 2 on die 2, my sum would be a 3. A 2 and a 2 would give me a 4. A 3 and a 2 would give me a 5. 4 and a 2 is 6. 5 and a 2 is 7. 6 and a 2, an 8, right? So I'm just adding up these two numbers on the margins across the top and across the left-hand side to get the sums in the middle. So fill in your table as I'm filling mine in too. 3 and a 3 is a 6. 4 and a 3 is a 7. 5 and a 3 is an 8. 6 and a 3 is a 9. 1 and a 4 is a 5. 2 and 4 is 6. So now if I had a 1 and a 5, that would give me a sum of a 6. 2 and a 5 would be a 7. 8. Hopefully you're starting to see kind of a pattern here. So if die 1 is a 1, die 2 is a 6, this would be a 7, 8, 9, 10, 11, 12, right? So my possible outcomes, like we said, the lowest sum I could get is a 2. The highest one is a 12. But you can see there's a lot of ways that I could get all these different outcomes. In fact, remember we said the multiplication principle. I'm going to roll die 1 and I'm going to roll die 2, right? How many different outcomes do I have on die 1? 6 different outcomes. How about die 2? 6 different outcomes. 6 times 6 is 36. There's 36 different possible outcomes in this table here, right? So that would have been hard to kind of list them all if I didn't make some kind of like an organized table like I did here, okay? But now I can see that, like we said before, there's only one way to get a 12. There's only one way to get a 2. But there's a lot of ways to get a 7. There's a lot of ways to get an 8. There's only a couple ways to get an 11. So if I do this experiment, I would predict that I would get a sum of a 7 a lot more frequently than I would get a sum of, let's say, like a 2 or a 3. So now, based upon this, let's find some of the probabilities. What's the probability that the sum is greater than 4? So remember, the probability that the sum is greater than 4, that's the number of favorable outcomes over number total of possible outcomes. So I know this is going to be over 36, right? Greater than 4 would be 5, 6, 7, 8, 9, 10, 11, and 12. So count these all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All right, so that was a lot of accounting. That was kind of annoying. The other thing that we could have done, let me write this down first. So this should be 30 over 36. If I want the probability that the sum is greater than 4, I know I need to add up all these numbers, but the other way I could do it is subtract out what I don't want. So I don't want 1, 2, 3, 4, 5, or 6. So I could have just done 36 minus 6 to get 30, if that makes sense. All right, the sum is 6 or 11. So all these 6's here would be my sums, and then these 11's down here. Ready? Count these. So 1, 2, 3, 4, 5, 6, 7. So this is going to be 7 out of 36. The sum is neither 5 nor 9. So I want to get rid of my 5's and my 9's. So that would be a lot of counting, right? So instead, I'm going to add up how many 5's and 9's I have and subtract from 36. So I have 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 5's and 9's. So if I take 36 and subtract 8, I get 28 out of 36. And if you don't believe me, go through and add them all up. So this one, number 4, the sum is greater than 7 and less than 11. So greater than 7 would be, let me write this down first and think about like what we're doing here. So greater than 7, that would be like an 8, a 9, and a 10, because it has to be less than 11. Does that make sense? So I'm looking for an 8, a 9, or a 10. So let me count up how many 8's, 9's, and 10's I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 12 out of 36. All right, number 5, the sum is either even or odd. All right, well, think about it. Even numbers would be 2, 4, 6, 8, 10, 12, right? Odd would be 3, 5, 7, 9, and 11. So even or odd, every single number on this list that I have written in red here is either even or odd, right? So that probability would be 36 over 36. Or in other words, 1. Remember in the beginning we said if something is definitely going to happen, if I say roll 2 die and add them up, what's the probability that your sum is going to be either even or odd? You're going to be like, it's definitely going to be either even or odd, right? Okay, so the sum is 3 or 9. So go and add up all the 3's and 9's. 1, 2, 3, 4, 5, 6. So 6 out of 36. The sum is not 8. So not 8. Everything but 8. Again, it would be a lot of counting if I had to count up all these numbers. So instead, let me figure out how many 8's there are. 1, 2, 3, 4, 5. And I'm going to take those 5 out of my 36. So there should be 31 out of 36 that are not 8. Last one, the sum is less than 10 and greater than 5. So less than 10 would be like 9, 8, 7, 6, but it has to be greater than 5, right? So it's just those 4. So let me go up and count. So the 9's through the 6's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I got 20 out of 36. right? So that's it for these dice problems. But before I kind of wrap up, I just want to ask you a quick question. We talked about the difference between theoretical probabilities and experimental probabilities, right? Would all these probabilities that I found here, are these theoretical or are they experimental? So in other words, you have to say to yourself, is this what should happen in theory if I went out and rolled 2 die and added them together? Or is this what happened when my teacher actually rolled 2 die together and added them up? I didn't do any rolling, right? I just kind of mapped out in theory what should happen. So all of these are theoretical probabilities. That's awesome if you were able to recognize that. All right. Thanks for listening. That's it for today. Good luck with your probability problems.